Now that I've given you an overview of concurrent programming concepts, let's talk about how concurrent programs can be developed in Java. And in particular, we're going to talk about the features that Java supports to enable the use of concurrent programming. And we'll talk about threads, we'll talk about synchronizers at a high level, and then, of course, we'll get in much more detail later in other parts of the course. So the way that concurrency is implemented ultimately in Java at the moment is through something called a Java thread. And a Java thread is an object, which is an instance of class thread. And internal to the Java thread class are a bunch of methods and a bunch of fields. And on the right-hand side of the slide, I have a list of a whole pile of methods, not all of them, but many of the methods that are used in a Java thread. And if you were to look at the implementation of Java thread, which you can do because you can download the source code for Java, you would find that it's got a bunch of fields. And of course, it also leverages resources that are available inside the operating system and the operating system kernel to do various parts of the processing and various parts of the behavior. In particular, each Java thread has its own unique stack, its own unique set of registers, its own unique set of thread-specific storage, etc. And it's probably not a bad idea to remember what the unique features are in a Java thread, because those kinds of questions tend to show up on quizzes. A Java thread can also be in one of various states. So, of course, there can be multiple threads, but let's just focus on one thread at a time. So a Java thread starts out in the new state when you say new and make a new thread object like new my thread. And then once you call start, that transitions the thread to the so-called runnable state. Now, when you're in the runnable state, it doesn't mean you're running. It just means that you're capable of being run. And it's the responsibility of the operating system scheduler and the virtual machine and so on, the execution environment, to decide which threads to run and when. Obviously, those decisions will be different if you have one core or many cores, but it's the underlying scheduler's decision to move something from the runnable state to the running state. And once you're in the running state, then you can wait for various things. You can do timed wait for various things. You can block waiting for various resources to become available, things like mutexes or reentrant locks or semaphores and so on. And once you're unblocked, once you're able to go again, then you're put back in the runnable state. And then when the underlying scheduler decides it's your turn, you can be running. And at some point, your run method will return, either because it fell off the end normally or through an exception that wasn't handled inside of run. And that will cause the thread to become terminated. So those are just a bunch of different states. We're going to talk more about these states later, but for right now, just be aware that a thread can be in different states. Concurrent Java threads interact by sharing objects and or messages. And this leads to the two primary paradigms of concurrent programming or object-oriented concurrent programming that are supported in Java. The first approach is the shared object approach. And what that does is it basically has synchronizer objects, which are just good old Java objects, perhaps with a little native code thrown in to make them run faster. And they're used to synchronize the behavior of multiple threads to ensure certain properties. Most commonly, things like mutual exclusion. And all that means is that you only want one thread at a time to be in a so-called critical section of an object to make sure that the state that that object maintains is not corrupted. Any shared mutable state that's accessed, read and written, for example, by multiple threads accessing that object don't end up corrupting the state and causing weird problems like race conditions and other concurrency hazards. So that's the concept of shared objects, and there's a whole pile of them. So mutual exclusion is one of the key themes, which says don't allow corruption of shared mutable state when multiple threads are trying to read and write it. And we'll talk a lot more about mutual exclusion mechanisms shortly. Another thing you can do with shared objects is you can coordinate them, which says you want to make sure that the operations in the object occur in the right order, at the right time, and under the right conditions. And we'll see there's some synchronizers in Java that enable that as well. Here's a short laundry list of some of the key Java synchronizers. These include things like synchronized statements and methods, which are built into the Java execution environment. We have reentrant locks, which are class objects that are part of the Java class library and Java util concurrent. We have atomic operations, which are also classes defined that use really cool compare and swap operations. There's semaphores, there's condition objects, there's really low-level methods that do compare and swap operations that are really only available directly to people who are developing the Java class library itself. And we're going to talk about all of these mechanisms in this class, and you'll get some familiarity with pretty much all of them in the assignments we're going to do. The second paradigm is message passing, and that is a bit higher level abstraction that works by sending one or more messages from one or more producer threads, things that generate or supply data or objects or messages, to one or more consumer threads. And the way this works is by something called a thread-safe queue. And so that thread-safe queue has certain properties, like if the queue is empty and you try to get something from it, you can block until there's something in it. Likewise, if you try to put something in the queue and the queue is full, you can block until someone takes a message out of it, and so on and so forth. As you'll see, there's a whole pile of mechanisms that are available in Java to support message passing, including array blocking queues and link blocking queues, priority blocking queues, synchronous queues, concurrent linked queues. And once again, you'll get a chance to play around with a lot of these things as part of the course. I would be remiss, however, if I also didn't talk about the sharp edges and dark corners of concurrency. And both message passing and shared objects have some hazards associated with them. And you have to be aware of some of the things that can go wrong, even when you use the pieces of Java concurrency and synchronization that come out of the box. So we want to make sure when we program that we use the right patterns and practices to avoid these hazards. But here's a quick summary of the hazards. One type of hazard, which is all too common, are race conditions. And a race condition occurs when a program's behavior depends on the sequence or timing of the threads in order for it to operate properly. And we'll talk a lot about race conditions and what are some of the different conflicts that can arise if you don't synchronize your mutable shared state correctly. There's a program you can get that's part of my GitHub repository called BuggyQ, and it will demonstrate, if you run it in IntelliJ, just what goes wrong if you don't properly lock your objects correctly that are shared between threads. It's a great example to see very quickly and very definitively what happens if you don't do things correctly. And we'll take a look at that later. Another problem you can run into are so-called memory inconsistencies. And these occur when different threads have inconsistent views of what should be the same data. For those of you who are Star Trek fans, you're probably familiar with the concept of a transporter beam. And one of the key concepts there is you beam a person or an object atomically. You don't beam their head and leave their body behind. That would be a problem. For those of you who are Harry Potter fans, you're probably familiar with the concept of apparition and disapparition. And there's a concept in Harry Potter called splinching, which is what happens if you apparate your head but not your body, right? So those are examples of non-atomic issues that lead to inconsistencies. And we have almost exactly the same kinds of issues in modern hardware. And Java has mechanisms to avoid that, but you have to be aware of those issues. Here's a very simple example. We have a function called loop may never end, and we define ourselves a Boolean field that's mutable shared state, starting with the value false. And then we have a method called work, and thread T1 will sit there continually spinning while work is not done, while the Boolean is false. And down below, we have another method that could be called by a different thread to set the value of done. But if we don't do anything that involves correct synchronization, like we don't use volatile, which is a special qualifier of types, or if we don't use a synchronizer of some kind, this program may never terminate. And that has to do with memory inconsistency issues. And then the third and final hazard I'll outline here briefly is deadlock, which occurs when two or more threads are competing for the same set of resources, and one of them grabs onto one of the resource and tries to get the other one, and the other thread grabs the other resource and tries to get the first one. And here's a good example of this. Let's say that we have thread T1 that grabs lock L1 and then wants lock L2. And thread T2 simultaneously grabs lock L2 and wants lock L1. And what will happen here is they're stuck in what's called a circular wait or a deadly embrace. And neither one can make any progress because they both own a resource the other one wants, and they refuse to give it up. If you take a look at the link at the bottom of the page, there's an example on my website that shows how this can happen very easily with Java concurrency. So that's the end of just a quick overview of how concurrent programs are developed in Java. I don't expect you to take this information and go off and start doing programming assignment number 1. However, if you look at the video for programming assignment number 1, you'll see that it has links to other videos that explain other aspects of threads. We will start to talk about those other aspects of threads at the very beginning of our next class.